what we were talking about before was atoms and things like that. And the original idea for the atom was that basically you had a nucleus and you had electrons swirling around it. And the original theory was that these were circling around like planets around the sun. But then they had this problem. If you have a planet going around the sun, eventually the planet's going to spiral and it's going to get eaten up by the sun. So why doesn't this come in? And why do you get discrete levels? Why, like we were looking before with energy levels, why will electron be here or here or here, but can't be anywhere else in beside? Then about 1924, this guy by Louis de Broglie came along. He came up with quite a remarkable thesis in 1924. The thing was, de Broglie was originally a history student. He was doing humanities and decided later on to shift on to arts, onto maths and physics. So his bachelor's was in history, but his PhD was in physics. And what he was looking at Einstein's special relativity. He came to the conclusion, if light can act as a particle, if a wave can act as a particle, then particles can act as waves. And he actually did a PhD thesis on this, so showing that the wavelength of a particle is going to equal Planck's constant over the momentum. Planck's constant, and we'll probably be using joule seconds rather than electron volt, joule seconds over momentum. The reason why we're using joules is because this is going to be in kgs, meters per second. So, and that's going to give us a wavelength of meters. Now, the trouble was, when he produced this is really controversial work. But he was at predominantly an arts college, so there was nobody there that was actually qualified to mark this thesis. And one of the other problems was, so basically if they failed it and it turned out it would be good, they'd look like idiots. Or if they gave them a PhD and it turned out wrong, they'd look like idiots. And this is further complicated by the fact that Louis de Broglie was actually of a very high status noble family. So yeah, sort of Count Louis de Broglie. So, but thankfully one of the guys at the college actually knew, had a mate by the name of Albert Einstein who had a look at it and went, yeah, this is okay, so they gave him. So basically what we can say is if you have something like an electron has wave particles, and that means an electron, or even you or I mean this applies to all particles, has a wavelength. So let's actually try this. So if we have a de Broglie wavelength, what is the, I'm going to grab a fresh sheet of paper because it's going to chew up a bit of paper. So this is 9.1, is the de Broglie wavelength of an electron with energy K equals 10 electron volts. Now, so if it's got 10 a kinetic energy, this means it's moving. An electron has mass, it's moving, it's got momentum. Okay, this is pretty cool. So we know lambda is going to equal h over momentum. So in this case, h is going to equal, well, we're going to use, where is a good value for h? We're going to use 6.626 times 10 to the negative 34 joule seconds. So we're not using the electron volt value, we're using the joule second value. So we know what h is. It's over there. How do we work out P? Well, P is momentum. Remember, P equals mv. So, mass of an electron, we just look that up somewhere, is going to be 9.109 times 10 to negative 31 kg. So we just look that up. That actually should be on your formula sheet somewhere. If it's not, put it there. Okay, so we know the electron. So if we can work out the velocity, we can work out the momentum. Well, we also know the equation for kinetic energy. K is equal to half mv squared. So we know what K is. We'll have to convert that into joules. And we know what mass is because that's over there. So what we can do is we can rearrange this. So this goes to 2K over m, take the square root. It's going to equal V. Isn't that cool? So we better work out what K is. K is going to equal 10 electron volts times 1.602 times 10 to the negative 19, because that's the elementary charge. That equals, what's that? That's going to be, well, that's going to be 1.602 times 10 to the negative 18 joules. Yep. Okay, so if we put this in, so V is equal to root of 2 times 1.602 times 10 to the negative 18 joules, all over the mass of the electron, 9.109 times 10 to the negative 31 kgs. Again, this is calculator time, so we go 2 times 1.602 exp negative 18 divided by 9.109 exp negative 31, that's equal to some big number, take the square root of that, don't forget the square root, and that's going to equal 1.875 times 10 to the 6 meters per second. Okay, you'll notice that that's actually less than 1% of the speed of light, so we don't have to worry too much about that. So we don't have to worry about relativistic effects. So now we know what V is. So now we can stick this into the equation. P equals mv, which is equal to 9.109 times 10 to the negative 31 kgs, times 1.875 times 10 to the 6 meters per second equals times 9.109 minus 31 equals 1.708 times 10 to the negative 24 kg meters per second. And now we stick it into that final thing. So lambda is going to equal Planck's constant, h over p. Let's bring that up a bit, which is equal to 6.626 times 10 to the negative 34 joule seconds. So that's 34 all over 1.708 times 10 to the negative 24 kilogram meters per second. So it goes 6.626 x minus 34 so equals 3.878 times 10 to the negative 10 meters, or that's also equal to 0.3878 nanometers. So basically that is a very, very tiny wavelength. Now, so the question is, why is this relevant? And the thing is, let's go back to the problem. If we have an atom, here's our nucleus, a hydrogen atom, and we have an electron whizzing around the outside of this, this electron actually has a wavelength. And what this means is, to be in orbit, this electron must be a standing wave. And if you've done the standing wave experiments, you'll notice that at the fundamental frequency and the harmonics, you get a response, and in between there's nothing. So basically what this means is that the first level is basically equal to fundamental frequency, because that's the lowest state, that's the ground. The second, so if you get one wavelength around here, that's your n equals 1. So one wavelength. So basically n equals 1. If you can get two wavelengths around here, that's going to be your second level. If you can get three wavelengths around there, that's going to be your third level, just like the harmonics, exactly the same as the harmonics on the waves. So that means that these electrons can only exist in very specific bands or very specific locations. So remember what we're talking about when we're pumping energy in here, we pump energy in. If we have enough energy to raise it to this wavelength, up to the second harmonica, then it'll jump up to there, but nothing else. So this is really cool. This explains why electrons are in orbitals. Now the next question is, can we actually prove or demonstrate that electrons have wave properties? And the answer is yes. Remember the old two-slit experiment that we did, or Young's experiment? I don't know if Rachel did this with you, but if you send waves through there, what you do is you get constructive, destructive interference. And if we would put a screen there, we'll get light bits, dark, light, dark, light, dark, like that. Hopefully you will remember that. The thing is, if we send electrons through there, if we have an electron gun here, and we're shooting electrons through, we end up with exactly the same diffraction gratings. We actually end up with electrons here, 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 and none there. So we can actually say, yeah, that electrons act as waves as well as being a particle. So this happens down at the electron level. Does it happen up at the big level? I mean, do I actually ever run in danger of walking past the door and suddenly diffracting around the door frame? Is that a risk? How can we work this out? So let's do exercise 9.2. Let's figure out how big the de Broglie wave is for 9.2. Calculate lambda, the wavelength for a cricket ball. I was just watching Gale hitting 50 runs off 12 balls, so maybe he's hitting, I don't know, of 0.5 kg mass, moving at 45%, moving at 45 metres per second. So it's being tossed down the pitch by a really fast bowler. So how long would that wavelength be? Well, we'll do the same thing. Wavelength is equal to h over momentum. H, we were saying, is equal to 6.626 times 10 to the negative 34 joule seconds. What's the momentum going to be? So P is equal to mass times velocity equals 0.5 kg. We've got 45 meters per second, which is equal to 22.5 kg meters per second. And so now we've got H, we've got P, so we can stick this in. So it's going to be 6.626 times 10 to the negative 34 joule seconds over 22.5 kg meters per second. Calculate the time. 6.626 x negative 34 divided by, oops, not minus, divided by 22.5 equals 2.945 times 10 to the negative 35 meters. And the thing is that is such a short wavelength. And I mean, you or I walking around a place, we're going to have an even shorter wavelength than that because we may more. But that's such a short wavelength, you're not going to get any diffraction effects if you walk past the door frame. So, question is the electron a wave or a particle? The answer is yes. So sometimes an electron acts as a wave, sometimes it acts as a particle. Sometimes a photon acts as a wave, sometimes it acts as a particle.